Hi everyone, today we would be studying solid states. So the question is, why study solid states? What is the reason behind studying solid states? The answer to that would be, look around you. Almost everything that you see, the chalk that I'm writing with, the board that I'm writing on, or the laptop or phones that you're using to see me, almost everything is solid. So why has solid just to be a definition, a mere definition where you say solid is something that has fixed volume and fixed shape? Why not study solid deep inside? So our aim is to take the objects that we have right now and make them better. That's our aim as a society. So for that, what we do is we study deep inside the objects that we have. So let's say if I have a chalk right now, it's a solid, right? So if I want to study this, if I want to make it a dustless chalk, right now when I write with this chalk on the board, it gives dust. But what I want to do is I want to make it a dustless chalk. How do I do this? What I do is I study its structure. Or let's say if I want a material which has a specific electrical or thermal property, what do I do for that? I need to study solids so I can make such a solid. In this chapter, what we'll do is we'll analyze the structure of solids. How are the atoms, molecules, how all of these are arranged in a particular solid. And we'll try to answer questions like, let's say, this table. If I try to put my hand, this table resists my hand. I can't pass my hand through it, right? But if I try to wave my hand in this gas, I can easily do that. There's no resistance from gas. Why does it happen? So we'll try to answer these questions. Alright. So before going particularly specifically to solid, what we'll do is we'll study states of matter and what is matter. Then we'll move on to specifically solids. Okay, so let's start with matter. So what is matter? Matter is something which has mass and it occupies space. That's the simple definition of matter. Which has mass and it occupies space. So for example, table is matter, blackboard is matter, I am a matter, but thoughts, emotions, feelings, these are not matter. Reason why? Because they don't have mass or they don't occupy space. Alright, so discussing about matter. So firstly, what is states of matter? States is basically the form in which matter can exist. That's what states of matter means. So matter, so we have 5 states. Remember this, we have 5 states. So 3 are solids, liquids and gases. So these are generally what you have heard. The additional 2 are plasma and Bose, Einstein, condensate. These are the 5 states. So generally we have in normal form we have solid, liquid and gases. Those are the form that we study. At higher temperature and also Bose, Einstein, condensate is the man-made matter form. So plasma is something when gas ionizes. When gas ionizes, so the electron comes out of the molecules. So at very high temperature, like in the surface of sun or stars, this is where plasma is found. The state plasma. Also, you might see in hotel signs, neon lights, the hotel signs, there you will find plasma. So normally we study 3 states of matter that we have. So let's study these. So these are the matter that we have in normal condition. So this is solid, then we have liquid, gas. Alright. So the deeper question is, what makes a solid solid, liquid liquid or a gas gas? The answer to that would be, there are 2 opposing forces which are responsible for the state of matter. Alright, so let me write these 2 opposing forces, then we'll discuss about it. So 2 opposing factors. So the 2 opposing factors are intermolecular forces of attraction between constituent particles. And the second one is kinetic energy or thermal energy of constituent particles. Okay, so now before moving on, before discussing specifically these two terms, what I need to focus your attention on is constituent particles. So what are constituent particles? So let's study the term constituent particles, because this we would be using again when we discuss structure of solid particularly. So let's focus on constituent particles before that. So what are constituent particles? Constituent particles. So constituent particles, as the name suggests, are something which constitute a particular state of matter. So let's say we have solid, liquid or gas. So what are they made of? What are the constituents that make these structures, either solid, liquid or gas? So there are three constituents that we have of all everything is made of. So the three constituents are atoms, molecules and ions. Alright. So atoms we already know, molecules are a combination of atoms, and ions is what we get when atoms ionize. So when atoms either lose electron or they gain electron, they give ions. Alright. So what are these two opposing factors? So let's discuss this. So before that, let me show you something. So we have these four balls here. Alright. So these four balls represent atoms. So atoms, the constituent particles, we can have either molecules or ions, but for simplification, so we are taking only atoms. So what happens here? So these two opposing factors are responsible for the state of matter. What do we get? Either we get solid, liquid or gas. These two opposing factors are the factors that are responsible. So intermolecular forces of attraction between constituent particles. So these constituent particles, these atoms, they are attracted to each other due to intermolecular force of attraction. And the second one is the kinetic energy or thermal energy of constituent particles. So they have a kinetic or thermal energy due to their motion. They have kinetic energy. Where do they get this kinetic energy from? Due to thermal energy. Thermal energy due to temperature or due to heat. They have their own thermal energy. So there are two opposing factors. One is intermolecular force of attraction and the other one is the kinetic energy. Alright? Or the thermal energy, which makes them move apart because it gives them motion. So these are two opposing factors which are responsible for the state. Okay, so now let's discuss the state. So firstly, we have solid. So what happens in solid? In solid, we have strong intermolecular forces of attraction. So the atoms are close together. There's strong intermolecular force of attraction and the thermal energy is lesser. What happens due to that? So this closeness makes the solid rigid. As you see, it's all rigid. They can only vibrate at their own positions, but they won't move far away. So because they cling together, they stick together, they form solids, hard solids. Now what happens is, as you increase the temperature, as the thermal energy increases, so these atoms, they gain thermal energy due to temperature. As the temperature increases, they gain thermal energy. You see, now the intermolecular forces of attraction, they become weaker and the thermal energy increases. So as there is slight increase in thermal energy, the kinetic energy also increases. So now these atoms can flow. This is what happens in liquid. That's why you can see the liquids flowing. This is the reason. Now what happens is you increase the thermal energy more. You give higher temperature or higher thermal energy. Now what happens is the intermolecular forces are weakest now. Now this is what happens. One atom goes here, one atom goes here, and the two atoms are here. Alright? So the two atoms are here. So this is how far the atoms are. The reason is the intermolecular forces of attraction are weakest now. And the thermal energy has increased, and which results in increase in kinetic energy. So that's why the atoms are far away. This, you see the entire space, So this is the reason why gas has no specific volume or specific shape. Because now what you can do is, let's say if I apply a pressure, now you can close these atoms, you can take them together due to pressure. So what happens due to that is, gases don't have fixed volume or fixed shape. That is what you observe when you try to pump your bicycle tires. So the pump, what happens in the pump is, you compress the gas. Why are you able to compress the gas? Because the spaces between the atoms or molecules of the gas is way too high, so you can compress the gas. So that's the reason. Now this answers our question that we asked at the beginning of the chapter, that why I can pass my hand, why I can't do that, why I can't pass my hand through this solid. The reason being this, the atoms are so close together, or the molecules, whatever this table might have. So now I can't pass my hand through it, because it is a rigid solid that is there. But once it becomes liquid, I can pass my hand through it. That's what you observe when you try to put your hand into water. That's why it doesn't offer, it offers resistance, but it is not as high as solid has. But in case of gas, there's no resistance at all. So that's why you can move your hand freely, you can wave it. So that's the reason. Remember this, these two opposing forces, they are responsible for what the state of matter would be. Okay, so now what I want to do is, I want you to appreciate the air around you and see and feel this. The molecules of nitrogen, oxygen, all floating around you, and you see this vast empty spaces. Just feel that. Alright, so now what we want to do is, now we want to shift our attention on specifically solids. So solids, what we want to do is, we want to classify solids, as we have already established what solids are. Now what we want to do is, we want to classify solids. What are different classification of solids? Alright, so solids classification. So before that, why do we need to classify something? What does classification do? Classification gives order. What does order do? It eases our understanding. For example, you might have seen in periodic table, we classify as metals, non-metals. What do we have after classifying? We have specific properties. We can classify these. So we group objects so that our ease of understanding increases. So that's why we classify everything. So same goes for solid. Solids we classify based on two major factors. So one is the nature of intermolecular forces of attraction between constituent particles. You see the constituent particle terms comes again. So it's the same thing, either ions, molecules or atom, whatever the constituents are. So the second is based on arrangement of the constituent particles. So these are the two factors. So first is nature. What is the nature of forces, intermolecular forces operating between the constituent particles? Like let's say we have atoms or molecules. What is the nature of force that is operating between both of them? Alright. So now the second one is arrangement. Arrangement is how these atoms or molecules, how are these arranged? Do they have a regular arrangement or they have irregular arrangement? So based on that, the different classification is there. Okay. So now let's study this first, then afterwards we'll study that. So first is based on nature of intermolecular force of attraction. So based on that, the first one that we have is ionic. How much space do we have here? So we have ample amount of space. Okay, so now the second one is metallic. Third one that we have is molecular. And the last one that we have is covalent or network. And for this, let me draw a line here so that you have no confusion. So here is, we have crystalline, and the second classification is amorphous. Okay, so we'll study based on arrangement afterwards. So let us discuss this. So based on nature of intermolecular force of attraction, so how do we classify solids? So we classify them as ionic, metallic solids, then molecular solids, then the last one is covalent or network solid. Alright, so firstly, what are ionic solids? So definition for these is easy. Just remember what I'm saying, and so this will be easy. So what is the ionic? So ionic solids are those solids in which the constituent particles are ions. As simple as that. So what are the examples for that? We have NaCl, calcium fluoride. So, and the ions that we have, so we have positive or negative ion. Alright, those are the two kinds of ions we have. So positive, when an atom loses ions, it becomes, when the atom loses electron, it becomes a positive ion. When it gains electron, it becomes a negative ion. Alright, so that's simple. Those are ions. Alright, so there is no different a different concept what ions is. Ions are just atoms which have either lost electron or gain electron. Those are ions. And what are positive ions known as? These are known as cations. What are negative ions known as? These are known as anions. Now I'll give you a simple trick to remember this. So an ion, a negative ion is negative always, and cation, for cation you can remember this as your cat gives you positive vibes, so cation will be positive. Alright, that's simple. Don't ever get confused. Remember, this is not cathode anode, this is cation anion. Cathode anode is a different thing that we'll discuss in electrochemistry. Alright, so between cation and anion, what we have is electrostatic force of attraction. So that's the force that operates between the two. And the one thing to remember is, so when we have ionic solid, the ions, they have fixed position when they are in solid state. So they don't conduct electricity at all. But if we convert them into either a molten state or let's say in a solution, what happens then is the ions can move freely. What this does is it allows the solid to conduct electricity. Otherwise, in solid state, it is not a conductor of electricity. Remember this. Many times, many people will ask you this. They will say, ionic solid, do they conduct electricity? And the question you need to ask is, which state are you talking in? Is it molten or solution state, or is it solid state? Right? So now the example would be NaCl, the famous example. We have CaF2. Alright, so these two. Then we move on to metallic solid. What are metallic solid? Metallic solid are those solids in which the atoms are metal atoms. And the metal atoms, what happens in metal? Metal have the tendency to lose electron, so they form metal ions. Alright, so this is what happens. So these are the metal ions, so they have fixed position. So how do we get metal ions? Same. They lose electron, then they become ions. So these are atoms. Atoms, they lost electron. So the lost electron are here. So they lost electron, then they became positive ions. Alright. So now what happens is these electrons can move freely. You see? Because the positive ions, they are at the fixed place, but these electrons can move freely throughout the solid. So what this does is, it gives metal the property to conduct electricity, and they have very high thermal conductivity. That's the only reason, because the electrons, they can move freely throughout the solid. So they help in conducting electricity, and they help in conducting heat as well. And these positive ions, these are known as kernels. Remember this. And this electron, there is a sea of electron. Alright. And now the example for this would be copper, and basically the metals that we have. So molecular solid, how do we define molecular solid? Molecular solid are those solids in which the constituent particles are molecules. You see how simple definition this is? How simply we can classify solid? So molecular solid in which the constituent particles are molecules. So each constituent particle is a molecule. They are not atom, they are groups of atoms. Molecule, molecule, molecule. Alright. So now we have further classification based on what type of molecule is it. Is it a polar molecule? So we have polar molecular solid. Then is it one more thing, in metallic what we have is metallic bond. Okay, so now we have non-polar molecular solid. And the last one that we have is hydrogen bonded molecular solid. Okay, so in polar molecular solid, the constituent particle is a polar molecule. Simple definition. Just remember what we are doing. We are classifying the solids. All the solids that we have in this world, we are classifying them. And this is easy, you see. Okay, so now in polar, we have polar molecules. Example would be SO2 in solid state. Then we have NH3 in solid state. Okay, and now in non-polar, what do we have? In non-polar, we have non-polar molecules, and also we also have noble gases that we have, noble gas atoms, for example, argon. So these are also included in non-polar. All right. So in hydrogen bonded molecular solid, we have molecule in which there is a hydrogen bond. Alright, there is hydrogen bond between molecules, and the molecule, let's say if I take a molecule, in that we have hydrogen bonded to highly electronegative element. Alright, there is electronegativity difference. So what are the different atoms that hydrogen is bonded to in this hydrogen bonded molecular solid? Those are FON. So we have fluorine, oxygen, nitrogen. You can remember this as FON, FON. So this is simple. So now, what are the forces operating in polar? We have dipole, because there are two poles. Polar is positive and negative. In this, we have non-polar, we have London forces operating. And in hydrogen bonded molecular solid, we have only hydrogen bonding. Alright. So what example do we have? We have H2O. Non-polar for hydrogen bonded. For non-polar, what do we have? Non-polar, we have examples like CCl4. So that's a non-polar molecular solid. We have I2. Alright, so these are the examples that we have. Okay, now let's move on to covalent or network solid. So what are covalent or network solid? So in covalent solids, as the name suggests, we have covalent bond between the non-metallic atoms. Remember this simple definition. The atoms that we have, those are non-metallic atoms. And in that, between them, we have covalent bond. Now what happens is, let's say there's a carbon atom. Alright, let's say there's a carbon atom. Now carbon has a valency of 4. Alright, it requires 4 electrons to complete its octet. So now, carbon will form a bond with one more carbon. Also, this carbon needs 4 more, so this will form 4 carbons. So this way, there will be a covalent bond over the entire solid structure that is there. So what this does is, it makes a network. You see, each carbon attached to 4 other carbon, this carbon attached to, so it becomes a huge network. That's why covalent solids are also known as network solids. That's the only reason. And the examples for this covalent network solids are graphite and diamond. So these are the normal examples that we have. Alright. So crystalline, that arrangement, based on arrangement, we'll discuss later. Now what I want to do is, I want you to look at this table and just appreciate the beauty, and just remember this: all the solids in the world that we have are classified this way. Just see the power of the table that you have in front of you. All the available solids that we have are classified based on this. This is the whole classification. Okay, perfect now. So now, what I want to do is, we want to discuss graphite and diamond. So this is important. So I want to just give you a feel of what graphite and diamond, the difference between graphite and diamond, structurally of course, because the atom that they have is the same, that is carbon. They are made up of same carbon. But the question is, why is graphite soft as compared to diamond? What's the reason behind it? We need to see that. And also I'll show you why graphite is slippery as well. Okay, so now let's discuss it. We have graphite here, diamond here. Alright, so in graphite, you got to remember, in graphite we have one carbon atom attached to 3 other carbon atoms. Remember this. One carbon atom is attached to 3 other carbon atoms. Alright, in diamond what we have? We have one carbon attached to 4 other carbon atoms. One carbon attached to 4 other carbon atoms. Alright, so this is how it happens. Now let us draw this. So how graphite structure is, they are hexagonal rings, parallel hexagonal rings. So we have whole hexagonal layer, then below parallelly we have one more hexagon, 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 hexagon. I'll show you how. This will be much more clearer. So these are hexagonal rings. Alright. So these are regular hexagon. What does that mean? Regular means they have equal lengths. Alright. Just a moment. Okay. So these are the hexagons that we have. And below we have same hexagonal rings. Alright. So down we have same hexagonal rings. Alright. So this is how it is. Now see this, let's take any carbon. So these vertices, the point of intersections, these represent the carbon atom. So each carbon atom, let's say this one is attached to 1, 2, 3 carbon atom. You take any carbon atom is attached to 3 other carbon atoms. So this is a below layer. So carbon, as we discussed earlier, carbon has a valency 4. It has 4 valence electrons. That is, in its outermost shell, it has 4 electrons. So 3 it has already shared by covalent bond. The 4th electron is free to move, which is in between. So for each carbon, the 4th electron, and also below, the 4th electron is in between this region. So what this does is, it gives carbon, it gives graphite the ability to conduct electricity. Alright. So because the free electron, it can move, so this makes graphite a good conductor, which is not the case in case of diamond. So I'll show you how. Alright. So let's draw the structure of diamond. What happens? We have one carbon atom attached to 4 other carbon atoms. So this is a tetrahedral. That's how it looks like. Alright, this is how it happens. So let's take any carbon atom. We'll discuss this carbon atom. So this is attached to 1, 2, 3, 4 other carbon atoms. So that's how the whole structure goes. Alright, so that's why this, we don't have any free electron. That's why it doesn't conduct electricity. This, it has free electrons. Now, what we want to do is, we want to discuss about why graphite is slippery. Okay, so graphite is slippery because if you look at the 2 layers that we have drawn, so these 2 are this way, alright. So hexagonal ring all the way, and then in the down layer we have hexagonal rings all the way. So now we don't have a bond here. So what this does is, it makes graphite slippery. Alright, these 2 layers, they can slip over each other. What this does is, it makes graphite a good lubricant. Because since it is slippery, so in many machines where we can't use liquid lubricants, there we use solid lubricants. Because it is slippery, it helps machines. So this is also known as solid lubricant. We'll study this later as well. So this is a widely used solid lubricant, graphite. And also one more thing that I wanted to discuss here is regarding this 3 other atom, 4 other atom. This is sp3 hybridized, this is sp2 hybridized. And to remember this, there's a simple thing. So as diamond is more costlier, it's costly as compared to graphite. So we have 4 atoms. This is cheaper graphite, so we have only 3 atoms. Alright then. So I want to show you something. You might have done this before. You have been doing this since your childhood, but you don't see one thing. I want to show you something so that you remember this. So now this pencil that I have is a graphite pencil, right? So when I'm shading on this, see this. I'm shading on this. So what is happening right now is this layer, the lower layer that is there, it is coming off from the graphite. So this is how the structure is. The lower layer comes off and it sticks to the paper. You see how beautiful this is? The lower layer of graphite, when I'm shading with this pencil, the lower layer comes on this paper. So that is what is happening. So these are beautiful phenomena that you come to know once you study the structure of solid. Okay, so now what we want to do is we want to move. So before that, let me give you one more information. So this is 154 picometer, the bond length, and this distance, the distance between 2 layers, is 340 picometer. And this, let's say you can take, because these are regular hexagons, this is 141.5 picometer. So this is bond length. Alright, so this is distance between layer, and this is also 154 bond length. Okay, so now what we want to do is let's discuss based on the arrangement of constituent particles. So everything that we have done is based on intermolecular forces of attraction. Now let's study based on arrangement. So based on arrangement, how do we classify? So based on arrangement, we classify them as crystalline and amorphous. So let's study these then. So based on arrangement, what do you mean? So when someone asks me, what do you mean when you say like based on arrangement? So based on arrangement, let me rewrite everything so we have space. So based on arrangement means, how do I arrange? How has nature arranged the atoms or molecules? So based on that, so based on arrangement of constituent particles. So based on that, we classify them as crystalline, and the second one is amorphous. So what are crystalline? So in crystalline, the constituent particles that are there, what are constituent particles? The atoms, ions or molecules. So they have fixed arrangement. The geometry that is there is a regular arrangement. For example, let's say if I have constituent particles, let's say atoms. So if I see this arrangement, so let's say this arrangement is there, like 2 cubes. So what does this mean? There's a regular geometry to the arrangement. Alright, so those are crystalline solid. In amorphous, there is no regular geometry. So I don't have this specified geometry arrangement. They are arranged in random order. There is no order. If there is order, there is short range order. So in this, so they are like properly arranged, ordered in pockets. So let's say here I'll have arrangement, then I'll have disordered arrangement, then maybe somewhere here I'll have some pocket of arrangement. So those are amorphous solid. Alright, so now let me rub this so that we have difference here. So in this, the first point is they have regular geometry, and the order is a long range order. range order. That is, through the whole region, through a very long range, they are symmetrically arranged. In this, amorphous is derived from Greek word which means shapeless, and the Greek word that we have is amorphous, amorphous. That's how we pronounce this. Most of the words that we have in English are either derived from Greek or Latin, because these were ancient languages through which English came. Alright, so amorphous, and amorphous we have, this means shapeless or no form. That is amorphous, and this is short range. Alright, now the second point that we have is they have sharp melting point. The question is, why do they have sharp melting point? They have sharp melting point because they have regular geometry. Since they have regular geometry, the strength of each bond that we have is almost similar. You can say same, because the structure is regular. So bond length is same, so the bond strength is same. What happens due to this is, let's say, what is melting? Melting is basically building, the bonds break. So the solid is there, the bonds of solid breaks. So that's when melting occurs. So when I have equal strength, the bond strength is equal. Let's say I have a temperature, let's say 600, at which the bond breaks. So at 600 degrees Celsius, each bond breaks because they are of equal length. So they break at a sharp point, 600 degrees Celsius, they will break. So that's why crystalline, they have a sharp melting point. But in case of amorphous, they don't have range of melting point, or you can say melts over a range of temperature. What does this mean? Because the geometry that is there, that is irregular. They don't have fixed shape. So let's say if there's a bond, this bond length might be weaker as compared to a stronger bond length. So if I reach at 600 degrees Celsius, the weaker bond, it might break easily. But the stronger bond, it might require like 50 degrees Celsius more or 100 degrees more. So that's why it melts over a range. So first the weaker bond will break, then the stronger bond will break. That's why it doesn't have a fixed sharp melting point like this, like crystalline. Then we have a property which is known as anisotropic. Alright, so what is anisotropic? So I'll give you example for that. So let's say we have crystalline solids. So crystalline solid, we have an order. So I'll show you one order. So this is just a random order, doesn't have any specific like meaning or something, because in crystalline we have orders. So that is what I'm trying to show here. So let's say, for example, this is a crystalline solid. Okay, this is a 2D figure that I'm drawing. So does this have an arrangement, an order? Yes, it does. Because this and these second and fourth, these all are same. Alright, so there is an order that I can see here. So what happens in anisotropic, there are few properties, few physical properties that when I measure in different directions, they give me different values. For example, resistivity or refractive index. Those are known as anisotropic solids. Why is crystalline and anisotropic? I'll give you the reason for that. So let's say if I measure something, any physical property. So if I go along this line, you see, I see a cross, I see a dot, then I see a cross. However, let's say if I move along this line, what do I see? I see cross, cross, cross. So along different line, along this line X and Y, I see different people. I see different atoms there. So due to this, if I measure any of the physical property, it will give me different value. Alright, because just because the arrangement is such, because there is a regular arrangement, it becomes anisotropic. But what happens in case of amorphous? There is no regular geometry. So what happens due to that? Since there is no regular geometry, they are isotropic. That is, if you measure the physical properties like resistivity or refractive index, they give me same value. Why? Because they don't have a specific order. So if I move in this direction or this direction of the solid, remember what we are talking, don't forget what we are talking about. We are talking about a solid, we are talking about a crystal. Alright? This is not a crystal, this is just a chalk box, but I'm just trying to make you, don't forget this. What we are doing is, we are talking about the structure. So this is crystalline, let's say. Then we have amorphous, which doesn't have order. So within this, we have the structure, order structure, within this solid. That is what we are talking about. Don't forget that. Okay, don't get confused. So isotropic. So now in isotropic means it has same value along all the directions. Just remember this, because many times people will feel, okay, that's a crystalline solid, so it has to be isotropic. No, it won't. It is anisotropic. The reason we have explained, just because of this property of order, it becomes anisotropic. Alright, so the fourth property that we have is cleavage. So what happens in cleavage, so if you try to cut a crystalline solid along a surface, what it gives is, it gives smooth edges, that is there. It gives smooth cuts, smooth shapes when you cut it. But in case of amorphous, there's irregular cutting. If I try to cut it, the cutting is irregular. There's no fixed or smooth shape. Alright, and the last point is, these are also known as pseudo-solids. Pseudo-solids or supercooled liquids. What? Amorphous solid. Right? Remember this. Pseudo-solids are amorphous or supercooled liquids. So supercooled liquids, so you might have seen glasses in the window panes. So in summers what you will see is window panes are thicker at the bottom. Why? Because it is not a solid. You might think from before classes that glass is solid, but it is not. You see why? You see this? Because it's supercooled liquid. That's what happens. So that's why it flows when there's temperature that is given. So it flows in summers. That's why the window panes are thick at bottom. Okay. So now we have discussed amorphous and crystalline solids. Now let's move on to SiO2. SiO2 is an interesting character that we have. And why do we discuss SiO2? Because SiO2 exists in both crystalline and amorphous form. So let's see the structure of SiO2, because many people have confusion regarding the structure. So this needs to be cleared, the structure of SiO2. Okay, let's study SiO2. The SiO2 is silicon dioxide. It is also known as silica. So it is major component of sand. Alright, so it is found in sand, SiO2. So naturally SiO2 exists in two forms. Crystalline form and amorphous form. So these are the two forms that SiO2 exists in. Crystalline form of SiO2 is known as quartz, and the amorphous form of SiO2 is quartz glass. Okay, so now let's discuss the structure of quartz. What is the structure of quartz? Where is the structure of quartz? So these are the regular hexagons that we have. So what are regular hexagons again? So regular is they are equal in length. So all of these lengths are equal. Okay, so now let's discuss it. So what is quartz? Quartz is a mineral, as we discussed earlier. So it's a mineral, so we are looking at its structure. What is the structure of quartz? So what is the difference between quartz and quartz glass? both are SiO2, but what happens is, in case of quartz, the molten state, it takes time to crystallize. Alright, the cooling is, slow cooling is there, that's why all the arrangement of atoms that is there, it's in regular shape. The SiO2 is arranged in regular shape. But in case of amorphous, there is no regular shape. The cooling is rapid. So the molten state of SiO2 cools rapidly. That's why the amorphous happens. So these both occur in nature. So nature, in this case, it cools the molten state slowly. So it gives time to the structure to arrange itself in a regular manner, in a symmetrical manner. But in case of amorphous, it doesn't give it time. There's rapid cooling. That's why the structure that is there, it's not regular. And remember, both of them are SiO2. Alright, so we are discussing quartz. So in this case, what we have done is, so let's say this is quartz crystal. So we are looking at this crystal from top view. So that's the view that we have. So the top view, from top we are looking. So this is the 2D view that we'll get. So that's the view that we get. So what happens is, so as we know, there are two atoms, silicon and oxygen. So at these vertices, we have silicon. So I'll represent these vertices by cross. So at every cross, we have silicon. Every cross, alright. So in between two silicons, we have oxygen. So this is how it is. So this oxygen is being shared by two silicon atoms. So that's how it is going on. So now, when someone sees this structure, we have silicon at the intersection and two shared oxygen. So when you see this, and this one also, so when you see this structure, you will say that the formula for silicon, for quartz should be SiO3, because that's what it sees. We see silicon here, then we have oxygen, oxygen, oxygen. So that's what it, so then it repeats. Then we have silicon again, then again the same. So the basic structure that you will say is SiO3. That's the structure that you feel that should be the chemical formula for this. But is that the chemical formula? No. Why? The reason for it lies in the structure of quartz. So I'll explain you the structure of quartz with the help of a model that we have. So this is how it is. So this is what we call a tetrahedral. Alright. So this is what happens. So silicon is at the center. That's where silicon is at the center. So all of them are not equal in shape. So silicon is smaller as compared to oxygen. Then we have 1, 2, 3 oxygen, and the fourth oxygen that is out of the board. I'll show you with the help of this. So 2 we have here, and the third oxygen we have here, and the fourth, this is silicon, and the fourth oxygen we have coming out of the board. So that is how the structure looks like. This is how the structure of quartz is. So the fourth one, this comes out of the board. So 1, 2, 3 oxygen, and the fourth one. And the silicon is in between, the cross. Remember this, cross is silicon, and the circle one is oxygen. Now what you might think is, the formula for quartz should be SiO4, shouldn't it be? Because we have silicon and we have 4 oxygen. So SiO4 is the formula that you might think. But is that the formula? No, the formula is SiO2. Why is that the case? The reason for that is, if you look at the oxygen atom, this oxygen atom is being shared by two silicon atoms. You see that? 1, 2. So in case of this silicon atom, what we have is only half of oxygen atom. Same this half, same this half. So for one silicon, we have 1, 2, 3, and the fourth half oxygen atom. So because this oxygen atom is being shared by two, so in totality, the part that this silicon atom gets is only half. So we have 4 into half. That's how many we have, 1, 2, 3, and the fourth. So we have in total 2 oxygen atom. Alright, 2 oxygen. So that's why the formula is SiO2. SiO2. That's the correct formula. Remember this, due to the structure variation, many people have this confusion. Don't have this confusion at all. This is simple. So due to the structure, each oxygen atom is being shared by 2 silicon atoms, and the 4th oxygen atom is outwards. This is simple. Alright, don't forget this. Okay, so now what I want to show you is the piezoelectric nature of quartz. Alright, and remember the difference between quartz and quartz class is both of them are SiO2, but nature gives quartz time to cool down the molten state. That's how crystals are formed. The molten state, it crystallizes, it cools down. So that's what happens. It gives time to quartz. In case of quartz class, there is rapid cooling. That's why it doesn't give it time to form arranged symmetrical structure as in case of quartz. So as I was discussing, so I want to discuss this term. This is piezoelectric. You call this piezoelectric or piezoelectric. Both of the pronunciation are alright. So what is piezoelectric? So piezoelectric are substances which when given mechanical stress, they produce electricity. Remember this? Okay. So what happens is, in case of quartz, the structure is a tetrahedral, right? So that's the structure that you have. So right now, what happens is, because due to tetrahedral structure, the net dipole of this is 0. So it doesn't have a net dipole. So that's how the tetrahedral structure is. So we have silicon by cross, then we have oxygen, oxygen, oxygen. These 4 oxygen, alright. So the net dipole is 0. So now what happens is, when I give pressure to it, that's what happens. Piezoelectric are those substances which give electricity when given stress. So when I give it stress, see what happens. So now these oxygen atom, these try to move upwards. So when pressure is given. So now the net dipole, that's how it happens. I'll show you what happens. So now when you give it pressure, after stress, this is what happens. This. Alright. These are oxygen atoms. This crosses silicon. So now the net negative charge, it shifts upward. Because the oxygen atom, due to pressure, they move sideways. That's what happens. And oxygen is more electronegative element as compared to silicon. Net positive is below. So that's why this negative and positive charge up and down, it forms 2 poles. So this is why they conduct electricity. And where do you see these? You see, when you see lighters, gas lighters, when you press them, that's when you see spark. The reason for that is this piezoelectric or piezoelectric property of the substance. When you press it, there is a net dipole that is created, negative or positive, whatever the molecule is. So that's why it leads to spark and it conducts electricity. Alright, perfect.